I know that you guys are probably all waiting with bated breath. You know, I really don't know what that phrase means. Maybe it means that your breath smells like bait. Anyway, I know you're all waiting and wondering, what happens when I add an amine to an aldehyde or a ketone? Well, wait no longer, for here is the answer. When added to aldehydes or ketones, amines form this type of compound, which are called imines, with the letter I at the beginning. If you're wondering what the mechanism of imine formation is, then look no further than this crazy blankety-blank slide, which I lifted from your book. I could talk you through it, but I have better things to do, like actually teach you something important. The point is, if you react an aldehyde or a ketone with an amine, it forms an imine. And what in the world can we do with an imine? Well, you'll see that the imine in this diagram is shown here. If you take that imine and treat it with a base, denoted here by this B, it will strip a proton on the carbon alpha to this imine carbon and generate this type of compound, which is called an enamine, also an enamine. I love the word enamine because it sounds like the Spanish word enemigo, which means enemy. Are you an amigo or an enemigo? Are you an amine or an enamine? Here's what enamines can do. Once again, I can begin with my ketone, and if I were in a circumstance where I wanted to generate or to alkylate at this alpha position, have a big long carbon chain of some kind, what I could do is treat this ketone with an amine, like this cyclic amine shown here, and then with base, and it would generate this enamine. If I treat this enamine with an alkyl halide, like this alkyl iodide, then the electrons in the nitrogen push down, and the electrons in this double bond come out and attack that carbon, attaching this alkyl chain here. You can take an imine like this and treat it with acid, and it will actually hydrolyze it or convert it all the way back to a ketone. So this is one way of being able to take a ketone and put an alkyl group adjacent to it. You convert it to an imine first by reacting it with an amine, and then let that imine be treated with a base to convert into an enamine, and then the enamine reacted with an alkyl halide, and then you hydrolyze it with acid. That was a very long sentence, but here is another example. I can take my ketone, treat it with this amine. It will generate the imine and then the enamine, which are not shown here, and then I can react that with this acid chloride, and it will acylate this group. After I treat it with acid, it hydrolyzes off the imine and gives me back my ketone. I think that's pretty cool. Imines are fairly reactive. Hence, there are a lot of useful things you can do with them. For example, if I take my ketone or aldehyde and treat it with ammonia or any other amine, I can generate my imine. Imines by themselves are traditionally somewhat unstable. But if I take my imine and then treat it in the same flask with hydrogen gas and palladium carbon, it will reduce this double bond down to a single bond by adding hydrogens to this carbon and this nitrogen, giving me this amine. Let's review this process. I can take a ketone, convert it to an amine, by first converting the ketone into an imine and then treating it with hydrogen gas and palladium carbon. This whole process from here to here is called reductive amination. Here's another example of reductive amination. This time I'm not beginning with a traditional amine. I'm beginning with an amine that has an OH on it, a hydroxyl group attached to the nitrogen. When that imine forms on the ketone, it gives me this type of compound, which is an imine, except that it has an OH coming off the nitrogen instead. This type of imine is called an oxime. When treated with hydrogen gas and palladium carbon, it also will give me out the primary amine. So this is an alternative way of generating the primary amine through an oxime intermediate. Oxime intermediates are traditionally more stable than imines, which is one reason why this approach is sometimes better depending on the individual circumstance. And now I have to share with you guys a personal anecdote. Some time ago I worked as a postdoctoral researcher in Colorado. One of my fellow researchers told me about a former postdoc in our research group who approached him one day and said, "Hey, I just learned about the coolest reaction. It's called reductive amination." Now this story is humorous to me because here was a guy who had a PhD in organic chemistry and had never heard of reductive amination before. And this is a reaction that we teach college sophomores. When I heard that story for the first time, I began to suspect that this guy might have received his PhD from one of those coin-operated claw machine games. So what happens when we add water to a ketone or an aldehyde? Well, water will have trace amounts of hydroxide in it. That hydroxide comes into the carbonyl carbon, thrusts the electrons up onto this oxygen, generating this intermediate. The negative charge on the oxygen then steals a proton back from the water in the solvent and gives you this type of product. This product is called a hydrate. I'll explain in a few slides why this kind of compound is useful. What if we add an alcohol to a ketone? Well, it behaves very similarly and converts this ketone into this type of compound called an acetal. And what is the mechanism? Well, first I begin with my ketone. I have to add trace amount of acid, the electrons on the oxygen in that ketone, and this could also be an aldehyde, by the way. Reach out and grab that acid, protonating the oxygen to give this intermediate. Once that intermediate is achieved, my alcohol will come in and attack at the carbonyl. Thus, the lone pair electrons on the alcohol oxygen come into that carbonyl carbon and push these pi electrons into that oxygen to neutralize the positive charge. That gives me this type of intermediate. At this stage, the electrons on this oxygen reach around and grab this hydrogen, thrusting these electrons into this positively charged oxygen to neutralize the charge. That then gives me this intermediate. At this stage, these electrons come down to form a double bond, and while doing that, kick off this H2O leaving group. That gives me this intermediate. H2O then goes into the solvent. At this stage, a second molecule of alcohol comes into the carbonyl carbon and thrusts these electrons into the oxygen to neutralize that charge. That gives me this type of intermediate. To get rid of this positively charged this positive charge on this oxygen, the water molecule that was generated in the previous step comes and deprotonates it and thrusts these electrons into that oxygen to neutralize that charge. That then gives me my final product, which is called an acetal, and releases protonated water, hydronium, as a byproduct. This source of acid can then act as the acid source to catalyze a second cycle of this reaction. I thought this would be a great time to throw some problems at you, just to review some of the reactions we've covered so far, and to show you that I care. I want you to figure out what the products are that I would obtain by reacting cyclohexanone with each of the following reagents. as I'm going to be giving you the answers to the first two of these questions momentarily. This might be a good time for you to pause the video and try these on your own before going on. So here's the answer to our first question. If I take a ketone and I react it with this amine, what product do I get? Well, you might remember that if I take ketones and treat them with amines, what I make is an imine. To keep a neutral charge on this nitrogen, I only want to have 3 bonds to it. So during the reaction mechanism, these 2 protons will ultimately be removed and released with this oxygen in the form of water. So this is the product that I get. Let's take a look at the next problem. If I take cyclohexanone and react it with this alcohol and trace amount of acid, what in the world occurs? Well, first of all, the alcohol will come into this carbonyl carbon, thrust the electrons onto that oxygen, while the oxygen itself gets protonated by the acid. This gives me this type of product. You'll notice that this product looks very similar to the acetal that we covered in the last slide. The difference, however, is that there is a hydrogen here on this oxygen instead of an alkyl group. This type of product is called a hemiacetal. The word hemi, or prefix hemi, means half. Thus, we could say that this is actually a half acetal. I think that if you say that quickly, multiple times, it gets funnier. If you continue taking this hemiacetal through the reaction sequence with this acid catalyst and more alcohol, it will ultimately make the complete acetal, which has 2 ethoxy groups here coming off of this carbon. I have not drawn that product in this slide, but I imagine that you guys can figure out that on your own. Here's another problem. How could I convert this starting material into this product? You might remember from our earlier lecture in the last video slide that if I want to convert an ester into a primary alcohol, I have to react it with lithium aluminum hydride. Unfortunately, lithium aluminum hydride will also completely reduce this carbonyl down to an alcohol as well. So the question is, how in the world can I selectively reduce just the ester and not this carbonyl compound? I'm not going to give you that answer right now. I will momentarily, but I want you to at least be thinking about it and wondering about it, so that when I tell you the answer in a couple of slides, it will actually stick. Because they're in the same column on the periodic table, sulfur reacts very similarly to oxygen. Thus, a thiol, which really is a sulfur-containing equivalent to an alcohol, will react with a ketone much in the same way that an alcohol will. So if I take a thiol, like this methane thiol, and react it with this alcohol and catalytic acid, I will generate a thioacetal. Once again, this is exactly the same as our acetal we were talking about before, except that instead of having oxygens here, I have sulfurs here. The mechanism proceeds virtually identically, except that I have a sulfur atom instead of an oxygen atom. Now this is an interesting reaction. If I have a ketone like the cyclohexanone, and I react it with a dithiol. Now a dithiol is a thiol that has a molecule that has 2 thiols in it. What occurs is one of these sulfurs comes in and attaches to the carbonyl carbon, thrusting the electrons onto this oxygen. This oxygen gets protonated enough to become a leaving group. And then the second sulfur, which is dangling off here, comes into the same carbonyl carbonate also and kicks off water. This ultimately gives you also a thioacetal. The difference between the thioacetal shown up here and this one down here is that the one on the bottom is a cyclic thioacetal. So the question you might have is, why in the world would I ever want to make a cyclic thioacetal? The reason is because you can take a cyclic thioacetal and react it with hydrogen gas and rainy nickel, and it will completely remove these sulfur atoms and replace them with hydrogen atoms. Why is that useful? Well, let's go back to the previous slide and imagine that I have this starting material, cyclohexanone. Let's pretend that I'm trying to make a product that doesn't have an oxygen here, but only has 2 hydrogens here. How in the world can I get rid of that oxygen completely and replace it with 2 hydrogens? Well, I can go through these 2 steps. I react this ketone first with a dithiol to generate a thioacetal. And then I take that thioacetal and treat it with hydrogen gas and rainy nickel to replace the 2 sulfur atoms with hydrogen atoms. The thioacetal used does not have to be a 6-membered ring like this. It can also be a 5-membered ring. So this cyclic thioacetal will also submit to these reaction conditions to completely replace these 2 sulfurs with hydrogen atoms. You'll notice that that would give me a 1, 2, 3, 4, 5 carbon long chain completely hydrogenated, which is this product, pentane. We now turn back to the question I brought up earlier. If I had this type of product and I wanted to only reduce the ester and not touch the ketone, what could I do? Could I treat this with lithium aluminum hydride and convert the ester into a primary alcohol and leave the ketone alone? The answer is no. Lithium aluminum hydride is a very potent source of H-, so the H- will go into the ketone as well and reduce it to a secondary alcohol. It will also go into the carbonyl carbon of this ester, ultimately producing this primary alcohol. So if I treated this starting material with lithium aluminum hydride, I would not get this product. I would have a single bond to an OH here and this primary alcohol here. So how in the world can I do this? Well, the way I do this is by using chemistry called protecting group chemistry, where I can protect a ketone from being reactive to lithium aluminum hydride, and then ultimately remove that protecting group later to give me back my ketone. I'm going to show you now how that's done. First of all, I want to mask this ketone as something that will not react with lithium aluminum hydride. What is that something? Well, I'm going to mask it as a cyclic acetal. So if I take this diol, ethane diol, and catalytic acid and react it with my starting material, it will react with that ketone exclusively and give me this cyclic acetal. It will not touch the ester, so the ester gets left as an ester. Now, cyclic acetals, and acetals in general, will not react with lithium aluminum hydride. So when I take this intermediate and treat it with lithium aluminum hydride, the lithium aluminum hydride will reduce the ester. After that ester is protonated with acid, the ester is converted to a primary alcohol, and this acid and water will hydrolyze this cyclic acetal down to a ketone. So what's the bottom line here? Well, I can once again mask this ketone as a cyclic acetal to protect the ketone from this lithium aluminum hydride. The lithium aluminum hydride will then reduce my ester all the way down to primary alcohol. And when I quench with acid, that acid hydrolyzes the cyclic acetal and converts it back into a ketone. So this is the way I would go about taking this starting material and converting it into this product, thereby preserving this carbonyl portion of the molecule. Here's another cool example. You'll see that I have an aldehyde here and a ketone. As it turns out, aldehydes are actually more reactive to attack than ketones. The reason for that is that they have a hydrogen here instead of carbons on both sides. A hydrogen is less bulky and is therefore less obtrusive to having groups come in and attack, which means that aldehydes will get attacked more prevalently than ketones. So if I wanted to selectively attack just my ketone with a Grignard reagent and not touch my aldehyde, what I could do is treat this molecule with this diol and acid. As it turns out, because the aldehyde is more reactive than the ketone, you can do this if you have only one equivalent of this diol. And it will only form the cyclic ketal, or cyclic acetal, with my aldehyde, and will leave the ketone alone. At this stage, I can now introduce this Grignard reagent, methyl magnesium bromide, and the methyl anion will come into this carbonyl, push the electrons up onto this oxygen, and then I protonate it with acid. It generates this tertiary alcohol and hydrolyzes this cyclic acetal back down to the aldehyde. So this is also a very useful way of selectively reacting with a ketone and leaving the aldehyde alone. I'll now introduce you to another reaction called the Wittig reaction. Please remember that this name Wittig is German, hence the W here makes a V sound, not a W sound. In other words, I don't want any of you to call this a Wittig reaction, or I will cry. It is called a Wittig reaction. Now, this reaction is supremely awesome because it converts a ketone into an alkene. So I want you to look at this. If I take a ketone and I treat it with this type of compound, it's a phosphorus that has some crazy crap on it. But the phosphorus is double bonded to a carbon. What ultimately ends up happening is this carbon that's doubly bonded to my phosphorus and this carbon that's doubly bonded to my oxygen get together and form a double bond between each other. The oxygen and the phosphorus end up bonding to each other and walking away. This is really a partner swap. It's kind of like the reality TV show Wife Swap. This carbon is married to this oxygen and this phosphorus is married to this carbon. They trade partners. The phosphorus walks away with the oxygen and these two carbons are now fused together as an alkene. Here's a really cool specific example of that. I've got my carbon doubly bonded to this oxygen. I've got my phosphorus doubly bonded to this carbon, and they're going to do a partner swap. The phosphorus and oxygen walk away, and these two carbons end up being doubly bonded to each other. You'll notice that this carbon here to the right also had two methyls attached to it, so they end up being still attached to it in the final product. Once again, this is a very cool way of forming alkenes. So what is the mechanism of the Wittig reaction? Well, I'm going to show you here. What ends up occurring is if you draw this phosphorus carbon double bond, you'll notice that it actually can be shown as two different resonance structures. If I have the electrons go onto the carbon, I can have a carbanion and a phosphorus cation. So that phosphorus cation is a true resonance structure for this phosphorus carbon double bond. When I've got this resonance structure existing transiently in the solution, the negative charge on the carbon comes and attacks the carbonyl carbon in my ketone. And then these pi electrons open up and thrust into this phosphorus, giving me this four-membered ring. These electrons then rearrange. These two electrons flip down like a trapdoor, and these two electrons flip up like a trapdoor, releasing my phosphorus-oxygen double bond and my carbon-carbon double bond as shown here. This will be our final topic before retiring this chapter. Thus far we've talked a lot about nucleophiles coming into carbonyl carbons, thrusting the electrons up onto the oxygen and generating this type of intermediate. If this negatively charged oxygen is protonated, it then gives this type of product. This type of addition of a nucleophile into a carbonyl is called direct addition or 1,2 addition. The reason is because we begin counting at the carbonyl carbon up to the oxygen. 1, 2. The nucleophile comes in at the 1 position and kicks the electrons up into the 2 position. So we call it direct or 1-2 addition. What if you have a ketone that looks like this? In other words, it has an alkene immediately adjacent to the carbonyl portion of the molecule. What in the world can happen there? Well, as it turns out, sometimes you can have the nucleophile, instead of adding directly to the carbonyl carbon, it will add into this carbon right here. You see this carbon that's colored blue here? If this nucleophile adds into this carbon, it flips these electrons over here like a door on a hinge and pushes these electrons up onto the oxygen. That gives me this type of intermediate. I hope you guys can see that. You're welcome to pause this and look at it a couple of times until this makes sense. Once you have this type of intermediate being generated, the electrons on this oxygen, you'll notice, can come back down here to form a double bond and push these electrons onto this carbon. See that? So this compound and this compound are resonance structures of each other. This negatively charged carbon then gets protonated when you quench the reaction with acid, ultimately giving you this product. So let's look at the net reaction again. If I start here with a ketone or aldehyde that has a double bond or an alkene immediately adjacent to it, a nucleophile can come in to this carbon and ultimately give me this type of product. This is the mechanism that this entire reaction traverses to get there. This is very different from the nucleophile adding directly to the carbonyl carbon, because it's not. It's adding to the carbon that's at the beta position to the carbonyl carbon. This type of addition is not called 1-2 addition, it's called 1-4 addition. Because if we begin counting at the carbon that gets hit by this nucleophile, up to the oxygen we can count 1, 2, 3, 4 atoms. So when the nucleophile comes in at this position, we call it a 1-4 addition. This type of reaction is also known as conjugate addition. Conjugate addition, just so you guys know, is also frequently called Michael addition, which is named after George Michael. Now, I'm actually just kidding. It's not named after George Michael. Not that any of my younger students really have a clue who that even is. It's actually named after its discoverer, a 20th century chemist named Arthur Michael, who, I've been told, was born into a family that was so rich that he could actually fund all of his own chemistry research without applying for any external grant money. Wow, what a life. So here's an example problem that I want you guys to look at. The following compound was prepared by a conjugate addition reaction between an alpha-beta unsaturated ketone and an alcohol. I want you guys to identify the two reactants. I'm not going to give you the answer to this right now, but I'll let you guys think about it, and we can talk about it more in class together. This concludes the This concludes Chapter 18. I invite you guys to take a break, go change your cat's litter box, and get some rest before going on to look at our next video presentation, Chapter 19, which will be posted shortly.